This meeting is being recorded.
In problem 1.10, we are asked to identify any polar covalent bonds. And to indicate this, we're going to use our delta positive and delta negative symbols in the appropriate location. So what that means is which one of the two atoms on the end of the bond would hold a slightly positive charge and a slightly negative charge. So that has to deal with electronegativity. So if you recall, let's go to our periodic table real quick here. Electronegativity increases in this manner here, with fluorine being the most electronegative atom. So let's go back here and just use that general trend to infer if there are any polar bonds, where they are, and where these dipoles would exist. So in molecule A, we have carbon-hydrogen bonds, and the difference in electronegativity between carbon and hydrogen is not going to give us a polar covalent bond. Remember, that's less than about 0.4 difference between these two atoms, but we see carbon and oxygen. This would result in a dipole created here. And we know that carbon is less electronegative, so that would have this partial positive. The oxygen would have a partial negative, and we'll continue down. So this carbon here would also be affected by the polarity of this carbon-oxygen bond, and it would also hold a slightly positive charge on this carbon. And then we'll just kind of follow this down, because this carbon would hold a partial positive charge because it's next to this oxygen. And finally, this carbon here. So we have this alternating positive and negative partial charges, and all of these polar bonds that exist between these atoms. The only place that we don't see the dipole would be here, right? So there's no dipole in between the carbon and the carbon. For molecule B, we're going to have nonpolar covalent bonds here, and our carbon-fluorine bond. We know fluorine's the most electronegative. That will bear this delta negative. Then we have our positive central carbon, and chlorine is also much more electronegative than carbon, so that will hold that partial negative charge. Then we move over here to magnesium, right, being in the middle, bonded to carbon, and then the magnesium also being bonded to bromine. So what we need to note here is that the most electropositive atom is our magnesium here. So this polar bond will have a negative charge on the carbon. These are all nonpolar bonds. And then we'll also have a negative charge on this bromine. So we'll have 3 partial charges in molecule C. Let's go to our molecule D. Now, we've always seen carbon bonded to hydrogen showing a nonpolar bond, but now we have hydrogen bonded to oxygen. So this actually would be a dipole, with hydrogen being more positive, oxygen being more negative, and then we continue along. This carbon would hold a partial positive charge because of this oxygen up here. That carbon in the middle holds a partial positive charge. That hydrogen there would also hold a partial positive. And then we go down here. The hydrogen carbon bonds aren't affected, but we see a dipole between this carbon and this oxygen. And then the last partial charge would be placed on this hydrogen. Molecule E, we'll look at the same considerations as before. Carbon to hydrogen, all of these bonds are nonpolar. Carbon to carbon, same thing. So really we have this carbonyl here, this carbon double bonded to oxygen, and that will exhibit a partial positive charge on this end, partial negative on that end. And last we have this chlorine atom in the middle. So that will definitely be positive, delta positive, right? By comparison to all these chlorine atoms, which would hold a negative charge. And remember, each of these bonds are dipoles, are polar covalent, but this molecule would actually have no net dipole. And we'll talk about that later on.